Going live. I am live apparently on YouTube, so please let me know if there are any video or audio quality issues. Otherwise, I'd like to get started. So, hi, I'm JJ. I'm a developer relations engineer at Deephaven Data Labs, and I'm here today to talk about a tournament format matchmaking for solo queue players in team-based games. It's an application of combinatorics in computing geared towards online matchmaking systems for video games. However, the principles that I'll talk about today can be applied to any team-based competition, be it video games, sports, board games, etc., so long as there's some sort of rating system that you have in place. So not only could this be used for online games, but maybe intramural sports if you have a way to gauge people's skill levels. So I want to talk a little bit about the motivation for why I decided to do this in the first place. So back in September of 2019, before COVID, I held a LAN tournament for the game Halo Master Chief Collection. For anybody unfamiliar with Halo, it is a first-person shooter that grew pretty widely popular back in the 2000s for the Xbox console. The Master Chief Collection has the first 5 Halo games remastered on it. And so I was able to get 16 people together with 4 consoles, 16 controllers, 4 televisions, 4 accounts to play on Xbox Live, and 4 copies of the game. And so basically we had all 16 people playing at once on 4 separate screens. So for team games with teams of 4, there was no screen peeking allowed, which is extremely important for those of you who, like me, grew up playing games in split screen mode. We all know how frustrating it can be when people are looking at your screen to find out where you are and what you're doing. So the LAN tournament was really fun, and it was a really great success. And in the week or 2 leading up to the tournament, I realized that I had a bit of a problem. I didn't know at least half of the people coming to this tournament. Not only that, but I knew basically nobody's skill level at the game. Halo is something that I played quite a bit when I was in middle school and high school, but nowadays I don't really play the game much anymore. So I kind of stink too. And despite the fact that this is a LAN tournament, so we were going to break players into teams and have an actual competition, I wanted to make sure that this particular LAN tournament was fun for everybody involved, regardless of their skill level. So I decided I was going to create a little piece of software that would place players into teams based on the results of a seeding match. So once all 16 people got there, we all played for a little bit just for fun to get warmed up. And then we played an official seeding match, which was a 16-person free-for-all. I collected the results of that seeding match, fed them into my program, and it gave me, and my program spat out the most evenly matched possible teams, 4 teams of 4 from the results of that seeding match. And so that's what I'm here today to talk about, is applying the principle that I used for my LAN tournament to online gaming itself, because I happen to be one of the people in the times when I actually get to play online games nowadays who I play on my own in team-based games, and I don't really get to participate in any tournament format matchmaking. So team-based online games nowadays are extremely popular. They come in a variety of different flavors. This list on this slide is not comprehensive by any means. These are just some of the most popular ones. MOBAs in particular are extremely popular. I believe all MOBAs are played in a 5v5 format. MMOs have team-based competitions. For instance, World of Warcraft has an arena PvP thing. First and third person shooters such as Halo, like I just mentioned, Call of Duty and that stuff, they all have team-based competitions. Battle Royale games can be played. Usually it's a lobby of 100 players. You can play in teams of 2 and 4, I think, though I don't play any Battle Royale games, so I could be mistaken there. And then real-time strategy games are also really popular, with Starcraft 2 and Age of Empires having 1v1, 2v2, 3v3, and 4v4 team game formats. One in particular on this list that I still play from time to time is Starcraft 2. And when you hop onto Starcraft 2 online, if you play 1v1, you have the option to queue up for a tournament. And so when you queue up for a tournament in a 1v1 format, it will place you in a lobby with 7 other players. It will then seed you based on a matchmaking rating on your account. and then off you go into the tournament. And if you win the tournament, you get a nice little trophy and an achievement, or if someone clicks on your profile, they can see, hey, you know, player, hey, JJ won this tournament one time, except I've never actually won a Starcraft tournament because I'm not very good. But that's okay. And but when I play Starcraft, I play the team-based games. I play the 3v3s and the 4v4s, and so I miss out on that tournament format matchmaking that, you know, I would really like to play in. So in terms of online gaming, solo queue matchmaking works as follows. It's pretty standardized nowadays. A player will open the game of their choice. They will choose whichever mode they want to play. For instance, in StarCraft, let's say I want to play 3v3. I'll enter the 3v3 matchmaking mode and I'll click search. It will then pull up players of a similar caliber and skill. And once enough players enter the pool, so in a case of a 3v3 game, once 5 other players of a similar skill to myself enter the pool, it will then place us into our own match. The pool fills and the match starts, and then we play, and there's a winner, and then, you know, wash, rinse, repeat. And that's great, and it keeps players coming back, but what it's missing is that competitive tournament aspect. And not only that, but the ability to get a trophy at the end of it and a little achievement that says I won a tournament. I don't play 1v1 StarCraft because not only am I not very good, but for anybody that does play StarCraft, it is a very intense and stressful game. And I think that playing with it with teammates kind of alleviates that, the intensity just a little bit. So I'm here today to talk about, you know, online matchmaking for solo queue players and introducing tournament formats. And so in order to do that, we need to apply the principles that I did for the Halo LAN tournament. And those principles are based in a field of math called combinatorics. So combinatorics deals with a lot of different things, but in the case of this team-based tournament format for solo queue players, the answers we need, the first questions we need to answer are: how many ways can a team of 2 players be made from a pool of 4 players? Or more generally, how many ways can a team of R players be made from a pool of N total players? And the answer is called a combination. I'll show some how you can figure that out, as well as a formula in the next couple of slides. And then the second question we need to answer is: how many ways can 4 players be split into 2 teams of 2 players? Or more generally, how many ways can N players be split into M teams of R players each? And the answer is called a combination of combinations. There was no real math formula for this going into when I first solved this problem, so I came up with one myself, and I have tested it pretty rigorously, and it has worked every time, so I'm 99% sure this formula is correct, but if you find a way to disprove it, I would love to hear it. So anyway, let's just start out with the simplest possible case of 4 players and 2 teams. So let's say you have players A, B, C, and D. There are 6 possible teams of 2 you can make from that. You've got AB, AC, AD, BC, BD, and CD. So there's 6 possible teams of 2 to make, and there are 3 possible ways you can match those teams of 2 up. So that is the combinations of combinations. You've got team AB versus CD, AC versus BD, and AD versus BC. And there's 2 important principles when it comes to combinations, the first of which is that order does not matter, which means that the team of players A and B is the same as the team of players B and A. And the second one is that replacement is not allowed, which means that the team AB cannot play against the team AC, because A is on both teams, and A cannot play against himself in one of these games. So on this next slide, here are the 2 formulas for combinations and combinations of combinations. So on top is the combinations formula. It is as follows. It is N choose R. That's one on the left there. That middle expression with the parentheses and the N over the R is known as a binomial expression. So N choose R is equal to N factorial over R factorial times N minus R factorial. And for anybody who doesn't know what factorial is, the factorial of a number describes how many ways you can order a set of N objects. So 4 factorial is 4 times 3 times 2 times 1, and it describes the total number that you can order a set of 4 unique objects, maybe a red marble, a blue marble, a green marble, and a yellow marble, or something like that. So when you do this for 4 players in teams of 2, you come up with 4 factorial over 2 factorial times 2 factorial, which is 24 over 6, which is, 24 over 4, which is 6. And so we showed on this previous slide that there are 6 possible teams of 2 from 4 players, so that math checks out with the formula. And then for combinations of teams of 2, That bottom formula is a little more complex, but basically you are going to calculate the number of combinations until you reach no players left. And then you're going to divide the whole thing by the total number of teams factorial. So for 2 teams of 2, it's going to be 4 factorial over 2 factorial times 2 factorial multiplied by 2 factorial over 2 factorial, 0 factorial, and that whole product divided by 2 factorial. And a little interesting tidbit that I always enjoy about math and combinatorics is that 0 factorial is 1 because there is still one way to order an empty set with no objects in it. So does the math check out? We already kind of tested this out for 4 players and 2 teams of 2. We saw that 4 choose 2 is 6 and 4 choose 2 is 3. And so generally speaking, are there more ways to create a single team than there are combinations of teams? No, absolutely not. It turns out that the combination of combinations grows much, much faster than the combinations by themselves. So for 16 players in teams of 4, which is what I was dealing with for the Halo LAN Tournament, you have the total number of teams of 4 that you can make is 1,820. So there are 1,820 unique teams of 4 that you can make. And then there are 2,627,625 ways that you can create 4 unique teams of 4. So if your player pool gets sufficiently large, this number will grow completely out of control. So for instance, for 64 players in teams of 4, you can make 635,536 unique teams of 4 players. And then if you want to arrange the 64 players into 16 teams of 4, there are approximately 5 times 10 to the 53rd ways to do that. And now that becomes a real problem, because what if you actually want to create a tournament from 64 players with teams of 4? It's not really feasible to check every possible combination of teams. Even if you had, a 10 terabyte hard drive, that's not even going to begin to come close to being able to store all of the possible combinations of teams. So how do you approach that problem? And that's kind of what I ended up doing over the last few weeks. I woke up one Saturday morning and I wondered if I still actually had the Halo Team Maker code that I wrote 3 years ago, and I found it, much to my surprise. And then as I looked back at it, I realized, oh my goodness, this is so slow. I could do this so much faster. And I'll talk a little bit about that in just a bit. So in Python, what do combinations look like in memory? So there is a baked-in module called itertools, which has a whole bunch of really cool functionalities, one of which is combinations. So itertools.combinations is a method you can use to create combinations from a set. So for instance, when you use itertools.combinations, it will actually create a generator object, and when you convert that to a list, it looks like a list of tuples. So let's say I wanted to make every possible combination of teams of, every possible team of 3 from players numbered 1 through 9. In memory, what that would look like is a list of tuples, which I have here. There's the team with 1, 2, 3, 1, 2, 4, 1, 2, 5, etc., all the way until you get through 7, 8, 9. As far as combinations of combinations goes, there is no baked-in method to do this. I will show one in just a little bit. I will also make sure to post that code so it's publicly available, so if you want to test it out for yourself, you're more than welcome. But what you end up with is a list of lists of tuples. So basically, the next step up from combinations is that if you want to create 3 teams of 3 from 9 players, your first one would be players 1, 2, 3 versus players 4, 5, and 6 versus players 7, 8, and 9. You could also have players 1, 2, and 4 versus 3, 5, 6, and 7, 8, 9, and so on and so forth. Excuse me. And so that will just keep going until you've exhausted every possible combination of combinations. So creating combinations in Python, calculating combinations, this code here, which I will show actually being used shortly, will calculate the total number of combinations as well as the combinations of combinations given a player pool of n and given a team size of r. So I showed a few slides ago the formula for combinations. This just implements that in Python. It returns the factorial of n divided by the factorial of r times the factorial of n minus r. And then the combinations of combinations, you're just going to perform combinations until you've exhausted all of your players. And so creating combinations, as I mentioned before, there is the itertools package, which has the combinations method, which will create a generator object. So this create combinations will simply return the list given n and r. And so if I create combinations from 4 players with teams of 2, we'll see that we have a team with players 0 and 1, 0 and 2, 0 and 3. This looks exactly like what I had before with players A, B, C, and D. Now, if I do combinations of combinations, this is where things get a little more complex. I'm not going to go too deep into this code right now, but basically, if you create combinations, every possible combination of combinations from 4 players and 2 teams, and teams of 2, you'll get, team 0-1 versus team 2-3, team 0-2 versus team 1-3, and team 0-3 versus team 1-2. I will, like I said, post this code for anybody to try so that you can check it out for yourself to make sure that it actually works properly. So with that out of the way, we need to come up with a criteria in matchmaking to make sure that all teams are as even as possible. Now, in standard online matchmaking, it will attempt to equalize the cumulative matchmaking rating, or ELO, or player ranking between 2 teams of players, which for 2 teams is fairly straightforward. However, you have to ask the question, how can you equalize the MMR between more than 2 teams of players? Say, for instance, in the LAN tournament, you may be able to make 3 teams that are very evenly matched, but then at that point, you're not really guaranteed that the 4th team is going to be evenly matched. And then additionally, how do you handle player pools that get sufficiently large? Because as we saw earlier, once you get a large enough player pool, say for instance 64 players in teams of 4, there are over 5 times 10 to the 53rd ways that you can create 16 teams of 4. So the method that I wrote up about 3 years ago is a brute force method. What it'll do is it'll create every possible combination of teams from all of the players. So in the case of my Halo LAN tournament, it will create a list of lists, which is a list of tuples, which is 2,627,625 elements long. It's this humongous list in memory. It will then calculate the average MMR, or in the case of the Halo tournament, the average, the results of the seeding match for every combination of teams, and then it determines the most even team combination by each team's proximity to the others in that particular combination of teams. Now, that is a really slow method, which I'll show in just a bit. And then the smarter method, so when I woke up, like I said, Saturday morning, kind of wondering, do I still actually have that code somewhere? I looked at it and said, this is great and all, but it's really slow and kind of simple approach. A smarter method that I wrote up is where it will create every possible team from the pool of players. So for 16 and 4, instead of creating that 2,627,625 items, it will create 1,820 possible teams. It will then calculate every team's average performance, where in online matchmaking it would use an MMR system, but for the Halo tournament it's just how many kills versus how many deaths you got in the seeding match. It will then rank the teams based on their proximity to the average performance of every player in the pool. It will discard the bottom. In my case, I use the bottom 90%. It discards the bottom 90%, keeps only the top 10% of evenly matched teams, and then it will attempt to make team combinations with the remaining 10%. So there's no guarantee that this will actually find a solution, but as I'll show in a bit, actually right after this, I'll show that it finds 5 evenly matched combinations. So I'm over here to my IDE, and let me just make sure that I'm sharing the right screen in this place as well. 1 second. There we go. Okay, so I have here, so I just want to show what the seeding results look like. They're in a CSV file. So I'm going to display them here in the IDE just so we can see what they look like. And I just want to make sure as well that my face in the corner is not going to cover the thing. So I have them in a CSV, So when we take a look at this table, we can see the results. And these are not the actual results from the seeding match that I had for the LAN tournament 3 years ago. I didn't keep those. I kind of wish I did. You can sort them in whatever order you want, but basically here's 16 players, and here's how many kills and deaths they had in a 16-person free-for-all beat-em-up match. So here's the brute force method that I wrote 3 years ago. Basically what it does is it will create every possible combination of teams, which is, again, 2,627,625 items long. It will then go through every single one of those and then calculate the total difference in in seeding results for each one of those teams. So I'll run this now. Take note that I'm streaming with OBS right now, which takes up quite a bit of my computer's processing power. This is going to take a little bit. When I don't run OBS, this usually takes between 25 and 27 seconds to do the whole thing. So it's pretty long, and it turns out that if you do this for more than 16 players, like I remember I tried it with 18 players in teams of 3, and it just took, I mean, I was waiting. I let it run in the background for like 30 minutes before I just gave up. But I run the code, and it will print out a bunch of stuff for even teams, and it'll show that the teams are nice and even based on the results of this seeding match. And it will also tell me how long it took, assuming it finishes. Again, I'm streaming on OBS, which tends to slow my computer down just a little bit. But then the faster method, when I'm not streaming on OBS, tends to take around 75 milliseconds. So if you go from about 25 seconds to 75 milliseconds, it's about a 350 times speed up. And if this doesn't finish in time, I'll just stop it and just show the quicker one so that it actually... and not only that, but the smarter method will get 5 possible even combinations of teams. None of them are guaranteed to be the absolute #1 most even, but they're all even, extremely evenly matched. And so what I envision for something like this is for people like me, and what I believe to be the majority of the player base of a lot of these team-based online games, is a way for players like myself to participate in tournaments without having to go through, attempting to join a clan or attempting to, meet enough other people to put together something like this, and a programmatic way to make sure that the teams are evenly matched so that every game is fun for both teams and for everybody involved. And it worked really well for the Halo tournament that I had. This is taking a while. Anyway, it worked really well for the Halo tournament I had. It was 4 teams of 4. Every team played each other, and every single set was played as a best of 3, and every single set that was played went to the 3rd game, so everyone had a lot of fun. We did a tournament style. I bought Hot Wheels cars for every member of the winning team, and then the losing team got baby food. I don't think anybody actually had any kids, so there was no reason for anyone to throw a match just to get some free baby food. Here we go. All right, so it took about 2.5 minutes while I'm streaming with OBS. We can see, I mean, the printout, I did not alter these printouts from what I had 3 years ago. It's kind of messy, but you can see team #1 overall win-loss ratio is about 0.9677, and then 0.9682, 0.9692, and 0.96, so on and so forth. So all of these are evenly matched. If I run the second one, so that took 163 seconds. If I run the second one, we can see that it does in about a half a second. When I'm not streaming, it's about 75 milliseconds. Now it's about 500 milliseconds, but there are 5 possible setups where you can see the total number of wins and losses. In the case of Halo, it's the total number of kills and deaths in the seeding match. So you can pick from any one of these 5, and all these teams are going to be evenly matched. And so that is my presentation. Before I open it up to any questions, I would just like to mention that Recently, I've been working on using Python with the Open Dota API. For anybody who isn't aware, Dota 2 is one of the most popular video games out nowadays. Its tournaments gather millions of viewers with tens of millions in prize pools. Hundreds of thousands of people play at the same time, and there's this absolutely awesome API I've been using to get data on live matches and to parse matches themselves as they're happening to maybe predict the outcomes. And so I'm hoping to give another talk on that because I'm really interested in the intersection of data science and video games. So please keep an eye out for that video. And with that said, I would like to open this up to questions if anyone has any. Sure, Andrew, go ahead. Mm-hmm. Yeah, that's actually an interesting point because there's a real problem with Smurfs in matchmaking as well as teams. A lot of games don't have specific dedicated systems to pairing up only people who are solo queuing. So you may, let's say for a MOBA, it's 5v5. You get put with 4 other random people who are also solo queuing, and then the system says you can play these 5 people that are playing together that are at your skill level, except they have communication over voice and they know each other and have played with each other before, so it creates a discrepancy. And I'm sure that there are ways that some game companies have employed as an attempt to mitigate that problem, but that's not something that I considered. But it would definitely be an interesting one to try to solve too. Mm-hmm. Yeah. Yeah. So yeah, no, I mean, this is, like I said, it was fun to work on when I was actually doing the Halo tournament, and woke up a few weeks ago and I was like, man, I wonder if I still have that stuff that I did. Okay. So most online matchmaking systems will divide their online servers into time zones. So, for instance, I'm familiar with Starcraft, familiar enough to know that there's 4 servers. I don't think they discern based on specific time zones, but there's a North America server, a China, an Asia, and a Europe server. I don't really know how you could um, place people based on their time zone specifically, but I have a feeling that there are systems intact. I know that for other games that I've played in the past, you can specify if you want to play on a server in the East Coast time zone versus the West Coast time zone. And doing so properly can reduce latency and stuff like that. So unfortunately, I don't have an amazing answer for that because I'm not too familiar with how it's done in practice, but I would imagine there's something. So in my code, I could not. Are we able to hear these Jake talking on the YouTube stream? By the way, Okay, yeah, let me repeat this. So the first question that I just talked about is how you incorporate additional constraints such as time zone or preferred partners. Preferred partners is another interesting one that I didn't consider. But as well, for the second question, this is how do you deal with matchmaking with very different MMRs, for instance, two medium players versus a great player and a poor player? I don't do that in this code. It was kind of a quick and dirty solution to the problem. Typically, online matchmaking systems will incorporate leagues. So you have, let's say, matchmaking. Your matchmaking rating can go anywhere from 0 to 1,000. They may divide that into 10 individual bands, 0 to 100, 100 to 200, and so on and so forth, all the way up from 900 to 1,000. So what you would do is you would really only allow people to be placed into MMR or into tournaments with players in your particular league. Maybe it's from 600 to 700 MMR rating. In theory, you could open so for typical team games like a team of 4 versus a team of 4. They tend to make those MMR bands fairly narrow. With a large enough player base, you can still find games pretty quickly with small bands of MMR. However, for something like this, I envision that you could expand those MMR bands up a little bit, just because you not only do you require more players to join in just to start everything up, but you also, since this is mathematically creating even teams, the discrepancy of MMR between players shouldn't matter as much. In theory, I don't know how well that would work in practice. I'd be very interested to see how that actually happens. So if that is it for questions, I'll close up this live stream and like to just thank everybody for coming. Whether you came here to watch live or you are coming here after the fact, I appreciate it. And again, keep an eye out in the future. If this was interesting, I am hoping to give a talk on the Open Dota API in the next week or two. Well, thanks for coming, everybody.